Hello everyone, welcome back. This is lecture 25 of the lecture series Signals and Systems. In this video, the main focus will be on DFT, Discrete Fourier Transform. So, we'll see about frequency domain sampling of discrete time signals. Then we'll look at Discrete Fourier Transform. Then we'll see DFT as a linear transformation. And we'll finally conclude with properties of DFT. So, let's get started. So, in the previous lectures, we saw about sampling of continuous time signals. Then we saw about sampling of discrete time signals. But in this, we'll see about sampling of frequency domain of discrete time signal. So, frequency domain sampling of discrete time signals. So for discrete time signals, we know for aperiodic discrete time, aperiodic discrete time signal, let's say it is something like this. We know that our frequency domain representation is some x of e power j omega, and it is periodic with period of 2 pi. So 0, 2 pi, something like this, right? It is continuous and periodic. And how are they related? My x of e power j omega is equal to summation n equal to minus infinity to infinity x of n, let's say this is x of n, e power minus j omega n. Okay, so now we are saying we want to sample the frequency domain. But why is it necessary? Because all our computations are done on a digital signal processor. So in a computer, we are not performing any continuous time operation. Everything are discretized and they are digitalized. So if you have to perform a frequency domain analysis, sometimes we want to look at the spectrum, right? So then if it is an x of e power j omega, if it is continuous in omega, then we won't be able to perform it on a DSP. So what we do, there is a requirement to discretize the frequency domain. So this is the requirement, and we'll now see how it is done and whether the signals can be, the information is there any loss of information, or if the signal can be reconstructed faithfully, and everything we'll see. Okay. So now I have this x of e power j omega. And I want to sample it. Right? If I say I sample it. So since it is periodic, right? If I consider only the samples in the region of 2 pi, say samples in the region 0 less than or equal to omega less than 2 pi. So only if I consider this, it is sufficient. So if I say I take n samples, then I will call it x of e power j. Instead of omega, I will call it 2 pi by n into k. So my omega is 2 pi by n into k. Because and k is equal to 0 to n minus 1. So this says that there are n samples, which is from 0 to n minus 1. And they are sampled at a equal spacing, so we'll get 2 pi by n into k. So, and this will be equal to, if I substitute here, summation n equal to minus infinity to infinity x of n e power minus j 2 pi k by n into n. And as required, my k will go from 0 to n minus 1 since I'm considering only the samples in the region 0 to 2 pi. So now if I just elaborate this, so x of e power j 2 pi by n into k is equal to, so now n is going from minus infinity to infinity. So what I'll do is I will elaborate this in regions of n times, okay? Like multiples of n. For example, I'll consider n equal to 0 to n minus 1 as my first group. So it will be x of n e power minus j 2 pi k by n into n. So previously what would I have had? I'll have summation n equal to minus n to minus n plus of n minus 1, which will give me minus 1. And the same x of n e power minus j 2 pi k n by n. Similarly, on the right hand side, what will I have? Summation n equal to n to 2n minus 1 x of n e power minus j 2 pi k n by n and so on. So why I am writing like this is, if you notice this e power minus j 2 pi k by n into n. So if I replace n with n plus n, then you can see it is periodic. So e power minus j 2 pi k n plus n by n is nothing but e power minus j 2 pi k n by n into e power minus j 2 pi k. So this 2 pi k is anyway equal to 1 because it is a integer multiple of 2 pi, and we know that the exponential of minus j 2 pi into any integer is going to be equal to 1. So this will be equal to e power minus j 2 pi k n by n. So it is periodic. So what I can do is, in each of these I can replace this minus n with minus n. I have to make it 0. So what I have to do, I have to replace n with n plus n. Similarly, for the before case, what it would have been n to n plus 2n. Here it is n to n itself, n plus 0n. And here it will be n equal to n minus n. And the next thing it will be n to n minus 2n and so on. So what I can write it as summation n equal to 0 to n minus 1 and x of n I have replaced here with n plus n, right? So it will be n plus n e power minus j 2 pi k n by n plus, again this is periodic with any n, right? Any capital N shifting of n. So this I'll keep it same, plus this anyway we can retain, and here everything also will look like this. I'll get x of n plus 2n on the next term and 3n and so on up to infinity, minus infinity. And here it will be summation n equal to 0 to n minus 1 x of n e power minus j 2 pi k by n, capital N into n. Similarly, the next term will be summation n equal to 0 to n minus n. Here x of n minus n e power minus j 2 pi k n by n and so on. Now if I try to add this all up, because the summation term is constant for me. So what will I get? I'll get summation n equal to 0 to n minus 1, and I'll have summation, let's say L equal to minus infinity to infinity x of n minus ln, right? X of n minus ln into e power minus j 2 pi k n by n. So this will be my x of e power j 2 pi k by n, and my k is varying from 0 to n minus 1. So now I can substitute this with some other variable xp of n. So just as a representation. So xp of n is equal to summation L equal to minus infinity to infinity x of n minus ln. So if you see xp of n plus n, if you take, it is nothing but summation L equal to minus infinity to infinity x of n plus n minus ln. So now I can actually replace, I can actually take n common and I'll have n minus L minus 1 into n. So I can replace L minus 1 with some k or some other variable m. And the summation, since it is going from minus infinity to infinity, summation will remain same. So m equal to minus infinity to infinity x of n minus m into n. But this is nothing but my xp of n itself. So my xp of n is going to be periodic. So xp of n given by this thing is going to be periodic in n. So xp of n is periodic in n. So if it is periodic, then I can write a Fourier series for this, right? So I can write xp of n as summation k equal to 0 to n minus 1 sum ck e power j 2 pi kn by n, and my n will be equal to 0 to n minus 1. And if you want n and n plus 1, it's going to be same, right? Because it is periodic. So this is your discrete Fourier series. So from this, if you want to find ck, what will be that thing? It will be 1 by n summation n equal to 0 to n minus 1 x p of n e power minus j 2 pi k n by n. And here your k is equal to 0, 1 to n minus 1. But if you compare this with this thing, so this thing is nothing but x of e power j 2 pi k by n is equal to summation n equal to 0 to n minus 1 xp of n e power minus j 2 pi k n by n. So if you compare this and this thing, what is the only difference you can see? Only it is a factor of 1 by n. Other than that, everything is same. So ck is nothing but 1 by n x of e power j 2 pi k by n. And my k will be from 0 to n minus 1. And if I have to find xp of n in terms of x of e power j 2 pi k by n, what will I do? I'll just substitute ck there. So xp of n is equal to 1 by n summation k equal to 0 to n minus 1 x of e power j 2 pi k by n into e power j 2 pi k n by n. And my n is equal to 0, 1 to n minus 1. So what does this equation say? This equation says I can reconstruct xp of n from x of e power j 2 pi k by n. But can we still recover x of n? Because we started with x of n, right? So we'll take an example. So let's say my x of n is having some L samples. Okay, then it is 0. So 0 to L minus 1. It has L samples. So now I am sampling my frequency domain using n samples. So we saw that then xp of n becomes periodic in n. So if we say xp of n for n greater than L, so what I will have? I will have this thing repeated. So 0, L minus 1 and some zeros, and again at n it will start to repeat. So this will be n plus L minus 1, again some zeros, then again 2n it will start again. So again in the reverse side it will start from minus n and go up to minus n plus L minus 1. So in this case, to go back from xp of n to x of n, what you have to do? So your x of n is nothing but your xp of n in the region 0 less than or equal to n less than or less than n, and 0 for n greater than or equal to n, right? But in the other case, if my n is less than L, this is for n greater than L. If n is less than L, then what happens? So you can see that this thing will start to merge. So this is L minus 1, this is 0, and let's say my n starts somewhere here. Then you can see my samples start to get merged, or we call it time aliasing. And then again my next sample will come here and it will start to alias. So finally you will have something other than what you started with. Right, this will be my xp of n for n less than L, and here x of n can no longer be recovered. So we call it time aliasing. So to recover x of n from x of e power j 2 pi k n by n, what is the condition? My n should be greater than or equal to L. Even if it is equal to, these zeros will not come, but it will directly start here, which is again okay for me because this condition is still satisfied. Okay, so I'll put it in words. The spectrum. So in other words, I say this is spectrum because if you have x of n, it means that you can also recover x of e power j omega. You can recover x of e power j omega, with which you started from earlier. Okay, so that's why I say the spectrum of an aperiodic discrete time signal, which is nothing but x of e power j omega with the discrete time signal itself is like with finite duration L can be exactly recovered from its samples at frequencies omega k equal to 2 pi k by n if my n is greater than or equal to L. So this is my condition. And how do you require to recover? You need to compute xp of n. And once you have xp of n, you can derive x of n as xp of n for 0 less than or equal to n, less than n, and 0 for n greater than or equal to n. So compute xp of n and then use it in this formula. And then compute x of e power j omega from this. And we can also directly express this x of e power j omega in terms of the samples. So we will see how that is possible. So first xp of n we got, right? So xp of n we got this as to be xp of n. So from this x of n also we can get. So x of n is nothing but 1 by n summation n k equal to 0 to n minus 1 x of e power j into 2 pi k by n into e power plus j, right? E power j 2 pi k n by n, and this is for 0 less than or equal to n, less than or equal to n minus 1. And what is my x of e power j omega? So my x of e power j omega is summation n equal to 0 to n minus 1, or here it is n minus 1. If x of n is like limited to L, then you can use L minus 1. But anyway, we'll go with n minus 1. Since even if it is limited to L, or for n greater than L and less than n, it is going to be 0, right? So we'll assume this, and we have x of n e power minus j omega n. That's it, right? So now what do you have? You have to substitute x of n. So x of e power j omega is equal to summation n equal to 0 to n minus 1, 1 by n summation k equal to 0 to n minus 1, x of e power j 2 pi k by n, e power j 2 pi k n by n into e power minus j omega n. So x of e power j omega is nothing but summation. If I take the k summation outside and n inside, I will have k equal to 0 to n minus 1. And only this term doesn't depend on n, so I can take it out. E power j 2 pi k by n, and 1 by n I will take it inside. So 1 by n summation n equal to 0 to n minus 1, e power j, or I'll say minus j omega into minus 2 pi k into n by n. So if you have to put all n, I'll get a factor of n here. So by n. So to see what this function is, we will first look at another similar function. Let's say p of omega as 1 by n summation n equal to 0 to n minus 1 e power minus j omega n. So what will this translate to is, since it is like a geometric progression, you will have 1 by n, 1 minus e power minus j omega n by 1 minus e power minus j omega. And this is nothing but if you take e power minus j omega n by 2 and from denominator minus j omega by 2 outside, you will have 1 by n sine of omega n by 2 by sine omega by 2 e power minus j omega into n minus 1 by 2. So this is similar to the sinc interpolation. So similar interpolation we saw in continuous time, right? But what is the difference here? Here instead of omega by 2 in the denominator, we have sine omega by 2. So it is going to be periodic, right? So since both the numerator and denominator are periodic, it is in itself going to be periodic. Because my x of e power j omega is periodic. So that is also a reason why this is periodic in nature and not like the continuous time case we saw. Okay. So now again comparing this with this signal is nothing but p of omega minus 2 pi k by n, right? So in my x of e power j omega, I can replace this function by this thing. So x of e power j 2 pi k by n into p of omega minus 2 pi k by n. And if you look at the nature of p of omega, so which is nothing but 1 by n sine of omega n by 2 by sine omega by 2 e power minus j omega n minus 1 by 2. So if we just look at this part, so if we try to plot it, we'll see that it is periodic in 2 pi. So if I draw from minus pi to pi, I'll have something like this. So this function will have n minus 1 0 crossings. So here you can see 1, 2, 3, 4 are there. So this I have drawn for n equal to 5 in interval of 2 pi. And you can also observe that your p of 2 pi k by n, if you substitute omega equal to 2 pi k by n, you will notice that for k equal to 0, it is going to be equal to 1 because both your numerator and denominator goes to 0. And you have to take a limit and then you will arrive at 1. And it is actually 0 for k equal to 1 to n minus 1. So that is why it is like acting like an interpolating function. So at that particular value, x of e power j 2 pi k by n, only that value is there. And in the next instant, you will have the next value of that. And likewise. So your x of e power j omega is always equal to x of e power j 2 pi k by n at instance of omega equal to 2 pi k by n. This is always true. And in all other places, it is just like a linear combination of this shifted versions of this p of omega, adding at that place to give what the original x of e power j omega was there. So whatever we did till now is to arrive at this topic called discrete Fourier transform. Or DFT. It is just a more compact way of writing whatever we have discussed till now. So nothing different. And it is called discrete Fourier transform because you are discretizing the Fourier transform. Discretizing the Fourier transform. So if my x of n is a finite duration discrete time signal with length L, then I choose some n greater than or equal to L, right, such that my DFT is valid. Then from x of e power j omega equal to summation n equal to 0 to, since it is L, I will just put L minus 1, x of n e power minus j omega n. Now if I sample it at n point, I will call it n point DFT. Then I will get x of e power j 2 pi k by n, right? Or I can equivalently represent this as x of k. Since it is discrete, right? I will equivalently represent it as x of k. And this will be summation n equal to 0 to L minus 1. X of n e power minus j 2 pi k n by n. And for convenience, instead of taking L minus 1, I will just replace it with the upper bound n. Because anyway, x of n will be 0 from L to n minus 1. So it will not change it mathematically. So n equal to 0 to n minus 1, x of n e power minus j 2 pi k n by n. And my k will run from 0 to n minus 1. And to get back x of n, what formula did we derive? So IDFT. So here we are not considering xp of n. We are directly going to x of n because we already know the relation between xp of n and x of n. It is just a periodic representation of x of n. So this we'll call as inverse discrete Fourier transform. So IDFT. So IDFT, we are finding x of n, which is nothing but 1 by n summation k equal to 0 to n minus 1 x of k e power j 2 pi k n by n. And my n is varying from 0 to n minus 1. And well, when L is less than n, from L to n minus 1, your x of n will be 0 when you solve for this. And you may ask, when x of n is duration L, is length L, why do we go for some n greater than or equal to L. Isn't it like you are storing like more information than required? Like more information than required, or is it like more storage than required, since it is giving the same amount of information, right? So let us go back what this n represents. So if you had the x of e per j omega, so you have something like this. So I'll consider only this minus pi to pi. So if I sample with just n equal to 2 points or 3 points, what will I get? I'll get 1 this and 0 here, right? This doesn't give me any information. Like if I have to visualize what frequency it is containing, this doesn't show me anything good, right? If I go n equal to 10, so I will have something like this. So to visualize, this is like of more better for the humans to visualize, right? So it just improves the detail of my x of e power j omega. So increasing n increases the detail of my x of e power j omega, or x of e power, the sample version of this. So that's why so extra L minus n zeros are added to my x of n, and this is called as zero padding. So if someone asks you why do you zero pad a signal, you have to tell them because it improves the detail of your x of the sampled version of your Fourier transform. So next let us see our DFT as a linear transformation. So in this case, if you see both my x of DFT and IDFT, it is of length n. So we'll just copy this and see what we can interpret from this. So this is my DFT and this is my IDFT. And if I just replace this by a function called Wn, so I'll call it e power j 2 pi by n. Then DFT I can write it as summation n equal to 0 to n minus 1 x of n Wn power minus kn, and my k is equal to 0 to n minus 1, and my IDFT is nothing but x of n is equal to summation k equal to 0 to n minus 1. Of course you have 1 by n factor, and x of k, and this will be Wn power kn, and my n is equal to 0 to n minus 1. Or in other words, we usually take Wn as e power minus j 2 pi by n. Then this will become plus and this will become minus. So this is just a convention so that your DFT is having this positive coefficient. So if you just write it as a matrix form, right? So if you have your xn as something like x of 0, x of 1 up to x of n minus 1. Similarly, if you have n as x of 0, x of 1 up to x of n minus 1, then how can you write your DFT as your x of k is on the left hand side? So you will have xn is equal to, you have a matrix kind of multiplication into your small xn, right? So I can write it as small xn. So what will be the matrix multiplication? So my x of 0 needs to be multiplied with wn power k into 0. Similarly, x of 1 will be wn power k into 1 and so on, right? So it will be wn power k into 0. Here k is 1 for the first row. So 1 into 0. wn into 1 into 1. And in another case, my index k itself starts from 0. So this will be 0. And similarly, wn 0 into n minus 1. And the second row will be wn. Here k is 1 and n is varying from 0 to n minus 1. Similarly, in the final case, my k will be n minus 1 into 0, wn into n minus 1 into 1 and so on into wn into n minus 1 into n minus 1. So this matrix I call it as my wn matrix. So my wn is nothing but, so all these rows if you see they are having a power of 0. So I can replace it with 1. Here I had wn power 1 and so on up to wn power n minus 1. And in the final row I have wn into n minus 1 up to wn into n minus 1 into n minus 1. So this is my wn matrix and my xn is given as wn into xn. If you have to find the inverse, I just have to take an inverse, right? So I'll take wn inverse into xn. But if you compare xn with capital Xn, it is nothing but my IDFT. And how are my wn's related? I have 1 by n extra factor and my wn is like minus kn. So I have to just do a conjugate. So my wn inverse is, I have a factor of 1 by n and I should do a conjugate. So this is the relation for wn. So my wn into wn inverse will give me I, but my wn inverse itself is nothing but 1 by n into wn conjugate. So my wn into wn conjugate is nothing but n into identity matrix. So doing it this way, I can easily compute my DFT and IDFT by just using a matrix multiplication. I needn't go over everything and keep adding everything for each k equal to 0 to n minus 1. I can just do one simple matrix and then multiply it easily. And this makes life a lot easier when it comes to computation in a DSP. So next we'll see at the properties of the DFT. Again, we'll consider only n point DFT when we are adding the signal or multiplying, right? We'll consider such that both the signals x1 and x2, let's say, are in the same point DFT, which is like n point DFT, okay? So I'll again take this and put it here just for reference. So my first property, and again I'll write it in terms of e power j. So that it is easier for you guys to understand. Okay, so my first property is periodicity. So if you see both xk and xn, they are periodic in n, capital N. So xk, x of k plus n is equal to summation n equal to 0 to n minus 1, x of n e power minus j 2 pi, k you replace with k plus n. So this will be nothing but e power minus j 2 pi k n by n into e power minus j 2 pi k n, sorry, only n. So this is equal to 1. So this will be summation n equal to 0 to n minus 1, x of n e power minus j 2 pi k n by n This is nothing but my x of k itself. So my x of k is periodic. Similarly, my x of n plus capital N is also equal to x of n. You can try to do this. And second is my linearity property. So I'll just define the convention. So x of n, I'll say DFT takes it to x of k. So if I have two signals x1 of n having DFT x1 of k and x2 of n having DFT x2 of k, then x1 of n, or I'll say ax1 of n plus bx2 of n will have a DFT ax1 of k plus bx2 of k. So this directly follows from the formula. So if you add x1 of n plus x2 of n, here in the summation you can take common and you will get ax1 of k plus bx2 of k. So very easy to prove this. So next one is shifting property. Let's say you have x of n and I shifted by some units n naught. So x of n minus n naught. So how will I write it in terms of x of n? So for this you have to take a look at what is happening. So you know that your x of n is going to be periodic. So you have 0 something here and something like this up to n minus 1, and that again from n you are going to repeat it, right? So now we shift this by n naught. So x of n minus n naught, what is happening? And you are only interested in the region 0 to n minus 1. Region of interest. So what happens? So what will come at 0? Whatever was at minus n naught will come at 0, right? So I have something like this, let's see. And wherever the 0 was, that will be at n naught now. Because this is the right shift, right? And again n minus 1, I'll have something here. And again n, I'll have whatever was at n naught. It will go into repeat. So again, this is my region of interest. So now my x of 0 is nothing but whatever was at x of minus n naught. But since x of n is periodic, it is also same as x of n minus n naught. Because n minus n naught will fall inside 0 less than n less than or equal to n. Correct? Given that n naught is less than n. Okay. So similarly, my x of 1 will be x of 1 minus n naught. So which is nothing but x of n plus 1 minus n naught. And so on. Right? So I can also write my x of n as, or x of this is some x prime of n. So I can write x prime of n as x of n minus n naught modulo n. So it is like a circular shifting. So let's say your n naught is 1, what will happen? This is going to come here and this is going to move here. So what it means is whatever is at n naught is going to be same as this thing, right? So I will just take this, circularly rotate and put it in 0 and then push all of them by 1 unit. If you have to push them by 2 units, I'll take 2 of them, put it in the front and then push them again. So that is how it is visualized. So I'll just show you from 0 to n what happens. So I'll take an example 0, 1, 2, 3. So this is x of n. Let's say I want to shift by 1 unit, x of n minus 1. So what is this going to be? So this one I'll take here. So my 3 is going to come to 0. Whatever was a 3 will come to 0. And my 0 will go to 1. And my 1 will go to 2. And whatever was a 3 will come to 3. Suppose I have to do a left shift. Then I have to do it in the opposite order. So whatever was at 0 will go back to 3. And whatever was at 2, 3 will go back to 2. Whatever was at 2 will go to 1. And whatever was at 1, it will go to 0. So this will be my left shift. So this I have done for n equal to 4. So there are 4 units. If you have some 0 paddings, then what will happen? The zeros also will move accordingly. Okay. So this is how you have to do the shifting in a DFT. It is same for x of k. See, x of n and x of k are related by each other. Just the only difference is here in x of n it is e power j 2 pi k by n. In x of k it is minus j 2 pi k by n. Otherwise they both are same, and this 1 by n factor also we need to take care. So that's why I haven't mentioned like time shifting on anything. This is just shifting I am calling. So x of n minus n naught is nothing but x of n minus n naught modulo n. So I can write it something like this. N minus n naught. And in below I write it as n. Similarly, x of k minus k naught, I can write it as x of k minus k naught under n. So this is shifting. So the next property we'll see is reversal. So reversal is nothing different. So in reversal what happens? Sorry, x prime of n becomes x of minus n. So here x prime of 0 is going to be remain at x of 0. But for other than 0, x prime of n is going to be x of minus n modulo n. And this is for n not equal to 0, right? Even for 0, if you put your modulo is anyway going to be 0. But just to represent, I have shown like this. So to see an example, okay, 0, 1, 2, 3. This is x of n. If I have to write x of minus n, what I do? So my 0 will remain same. And this will be like this. So 1, 2, 3 I have reversed. So if you have 0 paddings, then you will have that zeros here. Okay. And the other way to write this is nothing but x prime of n is equal to x of n minus n. Because if you say your n is always going from 1 to n minus 1, you can write this thing. And at 0 anyway, this will be x of n, which is nothing but x of 0 itself. So if we see the symmetric properties, for even what we have, so your x of n should be equal to x of minus n, which is minus n modulo n. Similarly for odd, you have x of n equal to minus x of minus n modulo n. Similarly, conjugate even, you have x of n equal to x star of minus n. Similarly, conjugate odd, you have x of n equal to minus x star of minus n into n. So this is nothing but purely real. No. So this is just conjugate even, right? So for purely real, what you will have? That anyways, that doesn't depend on your minus n. So you will have x of n equal to x star of n. And for purely imaginary, you will have x of n equal to minus x conjugate of n. But you have to represent from x of n, you just have to take only the real part. Then what you have to do? So first we will see only the even part, x e of n this should be nothing but your x of n plus x of minus n into n by 2. And your x odd of n is your x of n minus x of minus n by 2. Similarly, your x real of n will be x conjugate of n, x of n plus x conjugate of n by 2. Similarly, your imaginary part will be x of n minus x conjugate of n by 2. So if you write your x of n as x real part of n plus j into x imaginary part of n, and if you substitute it in the DFT formula, so DFT formula what you have, summation n equal to 0 to n minus 1 x of n e power minus j 2 pi k n by n, and your k is equal to 0 to n minus 1. So if you substitute this here, you will have summation n equal to 0 to n minus 1 xr of n plus j xi of n, and e power j, this you can write it as cos 2 pi k n by n minus j sin 2 pi k n by n. So if you multiply these both and take real part of x of k, you will get summation n equal to 0 to n minus 1. So xr of n into cos 2 pi k n by n, and this into this will be minus sign will come, and you're already one minus sign is there, so you will get plus xi of n into sine 2 pi k n by n. Similarly, your xi of k, you will have it as summation n equal to 0 to n minus 1 xr of n into minus j sin 2 pi k by n. So you will have minus sign xr of n sin 2 pi k n by n minus of xi of n into cos 2 pi k n by n. So now if your x of n is purely real, your xr of k will reduce to summation n equal to 0 to n minus 1 xr of n cos 2 pi k n by n, which means this is even, right? Because it's a cos function. No, but still your xr of n is not even. So if your xr of n is even, then your xr of k is even. And if xr of n is odd, your xr of k is also odd. So similarly, if for xi of n, if you see xi of k, it will be summation n equal to 0 to n minus 1. You will have only this part. So again you have you will have the sine part minus xr of n sine of 2 pi k n by n. So here sine is odd. So it means that if xr of n is even, this is going to be. And the other thing to notice, since xr of n is odd, if this term is fully odd, then you are summing it over the full entire interval, which means that your xr of k will become 0. Similarly here, if xr of n is even, small n, right? This is even, this is odd, so this total will be odd, and if you sum it over, this will going to be 0. So if xr of n is even, odd, your xi of k will be also be odd. The summation itself will be a positive, some number, but if you substitute k with minus k, only the sign is going to change sign, which means that this minus will become plus. So which means my x of k is odd. But here, since if you replace k with minus k, this cos will observe that minus term. So your XOR of k is even. So if you consider your x of n is real and even, your x of k is purely real, again is purely real and even. X of a is also real and even. But if your x of n is real and odd, your x of k is imaginary, right? Purely imaginary and odd. Okay, similarly you can do it for x of n being purely imaginary and even and purely imaginary and odd. So next we'll see multiplication of two DFTs and circular convolution. So we know that multiplication of two DFTs, if you take it in the time domain, it will be a convolution, right? Any Fourier transform, if you multiply and take it in the time domain, it is convolution. But here, since it is periodic in the time domain, we'll see have a circular convolution. And circular convolution. So if I have my x1 of k equal to summation n equal to 0 to n minus 1, x1 of n e power minus j 2 pi k n by n, and both are endpoint DFTs. So x2 of k equal to summation n equal to 0 to n minus 1, x2 of n e power minus j 2 pi k n by n, and I get a x3 of k by multiplying x1 of k and x2 of k. Then I need to find what is the inverse DFT of this. IDFT gives me x3 of n. I need to find what is my x3 of n. So I'll start by saying x3 of some m is equal to 1 by n summation k equal to 0 to n minus 1 x3 of k e power j 2 pi k m by n, and my x3 of k is nothing but summation k equal to 0 to n minus 1 x1 of k into x2 of k e power j 2 pi k m by n, and my x1 of k and x2 of k, so I'll substitute that. So I'll have 1 by n summation k equal to 0 to n minus 1. My x1 of k is summation n equal to 0 to n minus 1 x1 of n e power minus j 2 pi k n by n into, I'll take another variable l equal to 0 to n minus 1 x2 of l e power minus j 2 pi k l by n into e power j 2 pi k m by n. So I'll take this k summation inside, then what will I have? Summation n equal to 0 to n minus 1, this x1 of n, summation l equal to 0 to n minus 1, this x2 of l, summation k equal to 0 to n minus 1. I'll have e power minus j 2 pi by n into k, right, into n plus l minus m, right? So I need to solve this summation. K equal to 0 to n minus 1 e power j, I'll take minus term inside, 2 pi k by n into m minus n minus l. So if I have summation k equal to 0 to n minus 1, some a power n or a power k, then this is nothing but for k equal to for a equal to 1, I'll have this equal to n, and for anything else I'll have 1 minus a power n by 1 minus a for a not equal to 1. Now what is my a? My a is nothing but e power j 2 pi by n into m minus n minus l. My a power n is nothing but e power j 2 pi into m minus n minus l. This is just an integer multiple of 2 pi, so this will be equal to 1. So if I substitute that in this will be equal to 0. So my summation k equal to 0 to n minus 1 e power j 2 pi k by n into m minus n minus l is equal to n whenever this m equal to n plus l, right? Or I can say my L is equal to m minus n plus Pn. Or in other words, since I have a circular thing, right, this is nothing but my m minus n modulus n. And it is 0 for any other case of L, right? L not equal to m minus n modulo n. So now if I substitute that here, what will I get? I'll get n, and my L is nothing but m minus n modulo n, right? So this summation term also will go away, and what will I get? I'll get x3 of m is equal to 1 by n. I have summation n equal to 0 to n minus 1 x1 of n, and x2 I'll get x2 of m minus n modulo n into n. So this n and n will cancel. So I'll get x3 of m is equal to summation n equal to 0 to n minus 1 x1 of n x2 of m minus n modulo n, and my m is equal to 0, 1 to n minus 1. So this is called as circular convolution. So in normal convolution, you will keep one of them fixed and then you will rotate the other and keep shifting it. But here, instead of shifting, you have to do a circular shift. So that is the only difference. So let's do an example. So let's say my x1 of n is 2, 1, 2, 1, and my x2 of n is 1, 2, 3, 4. And if you write like this, we don't know which one is 0, right? So this can also be 0. So to indicate that, we use this arrow. So to indicate that this is 0. So if it is not in 0, then you have to rewrite it such that the notation is such that it starts from 0 to n minus 1. So this is a 4-point DFT, right? 4-point sequence, and we need to find the circular convolution of this. So circular convolution is usually written like this. So x1 of n point circular convolution into x2 of n. So let us start by finding this. I can write it out as a formula. Summation n equal to 0 to n minus 1. So that was the formula, right? Since this side I can use some other variable m. So I have x1 of n, x2 of m minus n modulo n. So if I have to find x3 of 0, I'll have summation n equal to 0 to n minus 1, x1 of n, x2 of 0 minus n modulo n. So which is nothing but my x1 of 0 into x2 of 0 plus x1 of 1 into x2 of whatever 0, 1, 2, 3 plus x2 of n, x1 of 2 into x3 of 2 plus x1 of 3 into x3 of 1. So what will this give me? This is 2 into 1 plus 1 into 4 plus 2 into 3 plus 1 into 2. So 2 plus 4 plus 6 plus 2. So this is 14. Similarly, my x3 of 1 is summation n equal to 0 to n minus 1, x1 of n, x2 of 1 minus n modulo n. So what is this? You reverse x2 of n and then right shift it by 1 unit. So if you reverse, so I'll write it down. So here x1 of n is 1, 2, 1, 2, 1. So here x2 of 1 minus n modulo n is. So you reverse what you will get? 1, 4, 3, 2, right? And you right shift it by 1. So 1, 4, 3, 2. You right shift by 1. What you will get? So 2, 1, 4, 3. So now you multiply these both and add. So we'll get 4 plus 1 plus 8 plus 3. So it is 12 plus 4, 16. So x3 of 1 is 16. Similarly, your x3 of 2 will be summation n equal to 0 to n minus 1, x1 of n, x2 of 2 minus n modulo n. So this just reversal plus right shift by 2. We already have right shift by 1. So right shift by 2 should be easy. So I just shift it right once. So 3, 2, 1, 4. And then you multiply. So 6 plus 2 plus 2 plus 4. So 14. So x3 of 2 is equal to 14. Similarly, the last one, x3 of 3. If you take, you will have summation n equal to 0 to n minus 1. And here again, you needn't write n minus 1 because you know what is n. The n here is 3. So this will be, n is 4 here. So this will be up to 3. x1 of n, x2 of 3 minus n modulo n. So this is nothing but 2, 1, 2, 1 multiplied with 4, 3, 2, 1. I'm just right shifting this by 1. So multiply this 8 plus 3 plus 4 plus 1. Again 12 plus 4 is 16. So your x3 of 3 is equal to 16. So what is your x3 of n? So it is 14, 16, 14, 16. 14, 16, 14, 16. So this is your circular convolution. So the last property, we'll see the Parseval's relations or Parseval's theorem. So the more general theorem is like this. So summation n equal to 0 to n minus 1, x of n and y conjugate of n is equal to 1 by n summation k equal to 0 to n minus 1, x of k into y conjugate of k. And the more general one will be where your y of n is equal to x of n. So you will have x of n modulus square is equal to 1 by n summation k equal to 0 to n minus 1, x of k modulus square. I am not deriving this because we have already derived Parseval's theorem for each of the continuous time and discrete time, and this should be straightforward to be derived. And you can also try to derive the duality relation. So you have your DFT x of k equal to summation n equal to 0 to n minus 1 x of n e power minus j 2 pi k n by n, and IDFT x of n is equal to summation k equal to 0 to n minus 1 x of k e power j 2 pi k n by n. So your x of n, if you take a DFT, you get x of k. But if you use this x of k as a sequence and then try to get its DFT, what will you get in terms of x of n, how it is related? So that is what we want to see. So you can take any of these both equation. So I'll take the IDFT equation. I'll get nx of n is equal to summation k equal to 0 to n minus 1 x of k e power j 2 pi k n by n. So I have to convert this e power j into e power minus j. So without affecting this x of k. So what I have to do is I have to replace n with minus n. So I'll get nx of minus n is equal to summation k equal to 0 to n minus 1 x of k e power minus j 2 pi k n by n. Now I replace n with k and k with n. So what I'll get, nx of minus k is equal to summation n equal to 0 to n minus 1 capital X of n e power minus j 2 pi, this anyway is same, k n by n. So for my x of n, what is the DFT in terms of this thing? It will be n times x of the reversed value of x of n, okay? So it is nx of minus k. So this is your duality relation. Okay, so this is a really very important topic. I would urge you to go back and read on this topic and also solve as many questions as possible. So we'll also be having a final session where we'll be solving some questions on DFT. So until then, take care guys. Bye bye. See you.